Hi, good morning. This is the chapter on electromagnetic induction. And before we get to the problems, I want to give you some ideas quickly. All right, electromagnetic induction is the phenomenon of inducing an EMF or inducing a voltage in a circuit because the magnetic field associated with it changes. So that is what electromagnetic induction means. And the basic law in this induction is called Faraday's law, according to which the induced EMF, E, or the induced voltage, is equal to negative of the change in magnetic flux divided by the change in time. So the induced EMF increases with the rate of change of magnetic flux. That means if the flux changes faster, you get a greater induced voltage. And the negative sign shows that the induced voltage is always against the change. And the EMF can be induced in three ways. First, by a changing magnetic field. Two, by changing the orientation of the coil. That means if you have a coil or a loop and you rotate it, the angle that the loop makes with the magnetic field is changing. Therefore, the flux passing through it is changing. And the third method is to change the area of the loop. And the diagram shows how you can induce a voltage by changing the orientation, okay, by rotating it. In fact, this one shows how it could be induced by changing the area, actually. Now, remember that the Earth's magnetic field is generally inclined, and it can be broken up into two components, the horizontal and the vertical. And you have to be careful in determining which of these components is being cut by the loop or the conductor when it is moving. For example, if you have something moving horizontally, then it is cutting the vertical component. But if you have a conductor moving vertically up or down, then it is cutting the horizontal component. This is the first problem. I just wanted to get to you, or let me show it to you like that. The problem talks about a coil that has its plane perpendicular to a magnetic field, but the magnetic field is pointing up. And in a certain time, the field is changed to one of 0.25 Tesla, pointing down. So you see that the direction of the magnetic field has changed. Now, magnetic field is a vector. So if the direction changes, that means it has changed from positive to negative. And that is why you have the change in magnetic flux density as minus 0.25 minus 0.68, which gives you a total change, but that is the change in field strength. And because of the definition, B is equal to phi by A, in order to get phi, you got to multiply the B with the area. And the area of a loop is pi r squared. So when you take that into account, you get the change in flux. And then by Faraday's law, E is minus of the change in flux by the time. The two negatives make a positive, and you get the answer as 0.053 volt. Now in this question, you can see that the diameter changes. It actually decreases from 20 to 6. Now because the area is decreasing, the induced EMF will produce a flux in the same direction because it does not want the magnetic flux to decrease. That's why you have the induced EMF producing a flux into the paper. And then by Faraday's law, E is d phi by dt, again B times dA by dt, because it's the area that's changing. So when you calculate that, you get the voltage, and that voltage divided by resistance by Ohm's law will give you the current. In this question, the car is driving through the Earth's magnetic field, and it's talking about the antenna. Of course, the radio antenna is vertical, so we know it is cutting the Earth's horizontal component. And the formula for induced EMF when a conductor moves through a magnetic field is given by the product of the magnetic field, which is the horizontal component, the length of the conductor, and the velocity with which the conductor is moving. Now to find BH as shown in this diagram, you have to take B cos of the inclination. That's why you have B cos 45, and then you get the answer as 0.8 millivolt, 0.8 millivolt. In this question, you have a generator that has 480 loops. It is square shaped, and how fast must it turn to produce a 120 volt peak output? The formula for alternating voltage is E naught sine omega t, where E naught is the peak voltage, the maximum voltage, and E naught is given by NBA omega, where N is the number of turns in the loop, B is the magnetic field strength, A is the area, and omega is the angular speed, which we have to find in this case. Excuse me. And therefore, omega is E naught by NBA. And when you put all those, and remember that for a square, the area is the square of the length. And then you get 9.39 radian per second, which if you divide by 2 pi, you will get the linear frequency, which is 1.49 rotations per second. This question talks about a back EMF, and back EMF is just induced voltage, which is given by NBA omega sine omega t, like in the last case where this is the peak. And when you rearrange this, you can see that E by B omega is a constant because number of turns, area, and the number of turns and area in this particular problem are the same. So this is a ratio set up here. E1 by B1 omega 1 is E2 by B2 omega 2. And then we can calculate B2 because initially the voltage was 85, then it decreases to 75. So that is your E1 and E2. And then the omegas are 1100 and 2300. And the strength of the magnetic field originally is not given, so you can only get the final magnetic field in terms of the initial one. So B2 is 42% of B1. This question is about a transformer, and we know that for an ideal transformer, the power in the primary is given by IP Vp, because electrical power is the product of current and voltage. Rearrange that to get the voltage in the primary. Power is given 75 watts. So when you divide that, you get 3.4 volt. And we know that it's a step-up transformer because the voltage on the primary is only 3.4, but in the secondary is 12. It is a step-up transformer because the secondary voltage is greater. And then by what factor is the voltage multiplied? Just take the ratio. 12 divided by 3.4 gives you 3.5. In this question, power is to be transmitted from a generator over transmission lines, of course. And you have to find the voltage at the generator end of the lines. The power reaching the town is the product of the RMS voltage and the RMS current, from which we can find the RMS current. That is in megawatts. That's why there is 10 to the 6 that's given. And this is the voltage that is reaching the town. Again, that was kilovolt, so it's 10 to the 3, and then you get the current. And we know that the output voltage is the input minus whatever is lost. Now, remember that this is what is lost there. That is the voltage drop by Ohm's law. When you multiply the current with the resistance, you get the voltage lost or the voltage dropped. Since we already know the current multiplied with the resistance of the transmission lines, you will get the dropped voltage. So at the generator end, we should have had 49,333 volt. But what reaches the town is only 45,000 volts. And then to find the lost power as a ratio, we know the lost power is I squared times R, and therefore take the lost power divided by the total times 100. So the lost power is I squared times R, and the total power is what reaches the town plus what is lost, right? So you get 8.8% of the power generated was lost. Now in this question, there is a rod moving with a speed, and the magnetic field is given, and you have to find the induced EMF. Now the induced voltage is given by the product of the three quantities: magnetic field strength, the length of the conductor, and the velocity. Multiply all those three that are given and you get the voltage induced. Now current by Ohm's law is voltage divided by the resistance. Again, the resistance is given and you get the current, 6.1 milliampere. And in the third part it says the external force needed to keep the rod's velocity. See, because energy cannot be created, we are getting all this induced voltage because we're doing mechanical work in keeping the rod moving. And therefore the force required is from the previous chapter, the force acting on a current carrying conductor is the product of the current, the length, and the magnetic field strength. We calculated the current, that's the length, and that's the magnetic field strength in Teslas. That gives us 6.4 times 10 to the negative 4 newtons. In this question, we have a generator rotating at a frequency 85, magnetic field given, number of turns given, and it says the RMS voltage is 150 volt and the RMS current is given as 70 ampere. What is the peak current? Now to find the peak, all you got to do is multiply the RMS with square root of 2. That's the relation between the peak current and the peak RMS current, okay? I mean the RMS current. It's the same as the relation between the peak voltage and the RMS voltage. You just got to multiply the RMS with square root 2 to get you the peak. So that's easy, 99 volt. And then we have seen this many times that the peak voltage is NBA omega, which must be square root of 2 times the RMS voltage, as I already explained. Now rearranging that, you get the area. Substitute all the given quantities. The RMS voltage is given as 150. You have the number of turns, you have the magnetic field strength, and you have the angular Now, you have to be careful. That's not the angular frequency. That is the linear frequency. 85 rotations per second, or hertz. That's why we have to multiply it with 2 pi to transform it into the angular frequency. Now, that's omega when you multiply it. I've shown it here. And therefore, you get the area as something convincing and practical, 1.3 times 10 to the negative 2 meters squared. Like I always say, after you get the answer, look at it and see whether it's practical, which in this case, it is. This is a direct question where you have to find the self-inductance of a solenoid. The formula for finding the self-inductance is mu naught n squared A by the length. Don't get confused between these two L's there. One is the inductance, the other is the length. Mu naught is 4 pi times 10 to the negative 7. 2800 turns, that's the total number of turns. Area is pi r squared, and so that's the radius in meters, and divided by the length in meter will give you the inductance in henries. And then the B part says how many turns would you need to generate the same inductance if the core were iron filled. So now you'll have to use the mu naught for iron. That's all. Make n the number of turns. Same formula. Make n the number of turns, and in place of mu naught, multiply 4 pi times 10 to the negative 7 with the magnetic permeability of iron, which is 1200. Because the problem says the permeability of iron is 1200 times that of free space, isn't it? So that's why you get that. So the answer is 81 turns.